let's talk about paper chromatography. In a paper chromatography setup, you're going to have like a wooden plate of some sort, and this is going to be attached to a piece of paper via a nail. Okay, so you're going to have this nail. Now, in other versions of paper chromatography, you might see like some sort of like clip to attach the paper to something, but just know that the paper is going to be attached to something, right? And this paper is basically going to be dangling over a container. So you're going to have this container, it's going to be dangling over it, and the container is actually going to be filled with water. So you have a piece of paper attached to a wooden board, it's dangling over some water. Now, paper chromatography is used when you want to separate a sort of, so let's say if I have like a substance, not a substance, but like a mixture of different substances. So let's say if I have this purple thing, a purple dot on my piece of paper, right? And it's a mixture of two things, all right? It's a mixture of something that's non-polar, right? So inside of my purple dot, there's this is a mixture of something that's nonpolar and something that is polar. And when there is a difference in polarities, it's very good to use paper chromatography because it can separate this mixture into its sort of individual components based on the difference in the polarity. And you might be like, what? How is that possible? Well, let's take a look at it. So as soon as the water touches this piece of paper, right? And this piece of paper is also called something known as the stationary phase. Stationary phase. And the reason why the paper is called the stationary phase is because it's just not moving, right? It's the thing that's not moving, right? It's the thing that you place your sort of mixture onto and it's not moving. And your water is something known as the mobile phase because, well, your water is actually going to be moving, all right? What's actually going to happen is you're actually going to dip this edge of the piece of paper, right, into the water. So you're only going to dip the edge of the paper into the water. But what's going to happen is the water is going to start creeping up, right? And this is due to something known as capillary action. Now, I'm not going to go over it in this video, but just know that, like, it's like when you're trying to like wash your face and use like a paper towel, right? The paper is going to spread throughout the paper towel, right? That's kind of what's happening here. This paper towel that you put inside of this water, the water is going to start creeping up this paper towel, and it's eventually going to get to our mixture. Now, water, as you may remember, water is polar. Water is polar, right? So actually, what's going to happen is as soon as the water creeps up this piece of paper, what's going to happen is that the polar component of my mixture is actually going to start following the water. All right. So let's say this orange thing. This orange thing is the polar part of my mixture. Okay. What's actually going to happen is because the water is traveling throughout my paper and water is polar, and well, what's going to happen is the polar part of my mixture is essentially going to follow the water, right? Because well, it's kind of like the saying like dissolves like, right? When you have something polar, like a sort of like polar solvent, right? And you dissolve a polar solute in it, it's gonna like dissolve, right? It's kind of gonna readily dissolve, right? It's kind of like that, except this time the polar thing inside my mixture is going to be following the polar water, right? Because they are going to be attracted to each other. While the nonpolar part, it's not really going to be attracted to the polar water, right? So what's actually going to happen is the nonpolar part of my mixture isn't actually going to move as far. It's not going to move as far up as the polar part of my mixture. So this is going to be the nonpolar part, and then the orange thing is going to be the polar part. And boom, you have separated my mixture because of a difference in polarity. Okay. Now you're actually going to be measuring how far these components actually go down the piece of paper. So what's actually going to happen is kind of before this whole experiment starts and everything, you're kind of going to mark the starting point for your mixture, right? So this is like the starting point for your mixture. And what's going to happen is the first thing you have to monitor is how far each component goes. So you see how the yellow component goes this far, and then the orange component goes this far. And the final thing you actually have to monitor is how far the water actually goes. So let's say if the water goes all the way up the piece of paper and it stops right here. So it stops right here. All right. I'm just gonna draw a line for that, but just know that when you're actually conducting the experiment, it can be like a little like curvy sometimes, or whatever. Let's just say this is like the best case scenario, and like the water is like completely straight down the paper. And what we're essentially doing is we're trying to find something known as the RF value. All right. Essentially, the RF value is going to be the distance traveled by the part of the mixture, by the part of the mixture, and it's going to be divided by the distance traveled by water. All right. So, for example, let's say if we're focusing on the nonpolar component of my mixture, let's say this traveled a distance of 1 unit. And let's say my water traveled a distance of, let's say, 3 units. So my RF value, well, it would just be the distance traveled by the part of the mixture. So it would just be this one right over here, divided by the distance traveled by the water. Well, that's 3 units. So my RF value would be 1/3. Let's do this for my polar part as well. Let's say the polar part of my mixture traveled a distance of 2 units. So that means that my RF value that was a horrible voice crack. My RF value would just be the distance traveled by the part of the mixture. So that's just going to be 2 divided by the distance traveled by water, which is going to be 3. All right. Two additional things. So, one thing is that every compound has a different RF value, meaning that you're able to actually identify the specific compound that's inside your mixture. And another thing is that when you mark out the starting point, aka like where your mixture, where you place your mixture in the first place, you got to do that with a pencil, not a pen, because the water can actually kind of make the pen sort of ink move, right? Let's say if this is like, let's say if I'm using a pen right over here, the pen can actually start mixing with the actual mixture, and then it can get carried away with the water and messes up the results. However, pencil, the graphite in the pencil actually does not dissolve in the water, so it will not affect the results of your experiment. Practice question time. You are doing this, and then when you're doing these types of practice problems, always want to make sure to pay attention to the stationary phase and the mobile phase. All right. Chromatography paper, this is polar. All right. Mobile phase, this is nonpolar. Which pigment will travel further up the paper and why? The thing to know is that if you're stuck on these problems, a good thing is to draw out one of these diagrams. So we know that the mobile phase is nonpolar, right? Now, if the mobile phase travels up the paper, well, if one of the components in your mixture is also nonpolar, that's going to travel with the nonpolar thing, right? So whichever pigment travels up further on the paper is going to be the thing that is more nonpolar, right? So that's going to be the pigment that is more nonpolar. So that's going to be answer choice C. If it's more polar, then it's not going to travel with the nonpolar thing. It's just going to stay where it is with the paper, right? Because our paper is polar, our chromatography paper is polar. Well, then if my substance is polar, it wants to stay with the paper, so it's not going to travel up as far. You're given a mixture of two unknown dyes. You perform paper chromatography using the stationary phase, which is polar, mobile phase, which is more polar. Okay. And after running the experiment, dye A has a higher RF value than dye B. So when dye A has a higher RF value than dye B, that essentially means is that dye A traveled further than dye B, right? If you have two dyes, right, and let's say dye A traveled this much, and dye B traveled, I'm sorry, dye B traveled this much. All right. All right. And then let's say the water traveled this much. All right. Notice how if you divide this value, right, the length that dye A traveled divided by the total value, you would get a higher RF value than if you divided this smaller value by this big value, right? If this was, let's say, this is 2 units, this is 1 unit, and the whole thing is 5 unit, well, 2 out of 5 is greater than 1 out of 5, right? So if something has a higher RF value than another thing, that means that they traveled further. And the thing that travels further, that's going to be the thing that has the most similar polarity to the mobile phase. So we said how the mobile phase is very polar, right? It's more polar than the chromatography paper. If the mobile phase is more polar and the thing is traveling with the more polar thing, that means dye A is also very polar, right? So I'm going to say that dye A is more polar than dye B. Remember, this doesn't mean that dye B is nonpolar. Remember, polarity is a spectrum. All this means is that dye A is more polar than dye B. It doesn't mean that dye B is nonpolar, right? Dye is more polar than dye B, so that means it's going to be more attracted to the more polar mobile phase, right? It's going to be attracted to the more polar water with the ethanol, and that's going to make it so that it moves along with the mobile phase. Here's a column chromatography sort of diagram. Column chromatography is another chromatography method used to separate a mixture based on the polarity differences inside the components of the mixture. So what you're going to have is, of course, you have your column, right? And the column is going to be filled with something known as silica gel most of the time. And silica gel is going to be your stationary phase. So unlike paper chromatography, where your stationary phase is the paper, column chromatography, your stationary phase is going to be the silica gel, and it's also going to be polar. All right. Now you don't want your silica gel to drain through, all right, because at the bottom here we have something known as a stopcock. This is essentially a valve, right? And if you actually turn this valve sort of 90 degrees, it's going to allow fluid to come out, right? Now I do not want my stationary phase to come out, all right? So what I'm actually going to do is I'm actually going to place a piece of wool at the bottom so that my stationary phase stays where it is, right? If the stationary phase starts traveling down, then the components of my mixture will also sort of start traveling down, and that's going to be bad. That's going to mess with the results. And that's not what I want. Now, of course, you can't have your column just floating in the air like this, right? It's kind of defying the laws of gravity here. So what's actually going to happen is you're going to have something known as a ring stand. So this is your ring stand, right? And it's going to have a sort of clamp. So there's going to be like a little clamp around it. Like you can imagine this in like 3 dimension, right? There's going to be like a clamp that's basically just there to hold the column in place. And finally, all that we kind of have to do is we just have to place our mixture in the mysterious mixture that we have. Actually, let's make the mixture purple. So this is going to be our mixture, and then finally we place something like a solvent up top. What the solvent is going to do is the solvent is going to allow it's going to allow the mixture to sort of dissolve in the solvent, right? And actually what's going to happen is the dye is actually going to start traveling down and it's going to get through the wool, right? The wool is actually not going to let the silica gel through, but it's going to allow the mixture of this let's just say this is actually hexane. Let's just say my solvent is hexane. And remember that the solvent, the thing that is kind of dissolving the dye, remember that's always going to be the mobile phase, right? That's going to be the thing that's traveling. And hexane is also non-polar. So what's actually going to happen is this hexane is actually going to dissolve the dye, and it's going to help it travel down. The dye is actually going to get past the wool, unlike the silica gel. It's going to get through the stopcock, and it's going to start draining out. Now, as the dye gets down, let's just say it separates into two components. Let's just say it separates into the yellow component and then the green component as it travels down with our hexane. So as our hexane sort of travels down, let's just say it separates into a yellow component and a blue component. Sorry, not blue component, a green component. Now, what inferences can you sort of make based off of what we said about paper chromatography? Because the green thing traveled down more, well, it's going to be more attracted with the mobile phase, right? So when the hexane moves down, the green dye is going to move with it because it has the strongest attraction to it. So you would say that the green thing is more nonpolar than the yellow thing, right? Green thing is more nonpolar because hexane is nonpolar, right? Meanwhile, the yellow thing, it's less nonpolar. It's actually more actually polar, right? The reason why we'd say that the yellow thing is more polar, well, that's because it didn't travel as far. So it's going to be more attracted to the silica gel, right? The stationary phase. It wants to kind of stay where it is. It wants to stay attracted to the silica gel. So um, that's kind of what's going on, right? The way I like to remember it is this is for either paper chromatography or column chromatography is the thing that moved the most. Well, that's going to be the mobile phase, right? It's going to have kind of this most similar polarity to the mobile phase, while sort of the thing that didn't move that much, the more stationary one, is going to have more of an attraction to the stationary phase. It's going to have similar polarities to the stationary phase, or at least similar polarities relative to the other dyes in the mixture. Now, what's going to happen is as these two mixtures travel down, even if it's very slow, you're going to see like a difference, right? You're going to see like this yellow part, you're going to see this green part, right? But both of them are still going to travel down. It could be a slow process depending on, because this yellow one's more attracted to the silica gel. But, you know, eventually what's going to happen is, let's say this green one travels all the way down here, and let's just say this yellow one travels all the way down here. What's going to happen is the green one is actually going to drain through this thing first. So you're actually going to see the green one drain through this thing first into the flask. All right. After the green one is completely done, right? So no more green, right? After the green one is completely drained through inside of my container, not container, Erlenmeyer flask, um, what's actually going to happen is you're actually going to swap the Erlenmeyer flask. So you're going to take this Erlenmeyer flask, place it to the side, and actually get a fresh new one. So you're actually going to place this Erlenmeyer flask to the side. This Erlenmeyer flask contains the green thing, and you're actually going to get a brand new Erlenmeyer flask. Now, this flask is going to be used to collect the yellow thing. So once the yellow thing drips through, it's going to collect in this flask, and boom, you have the two different sort of mixtures, or you have this mixture separated into its sort of individual components. All right. So when you're doing column chromatography, you do not collect everything in like one big container. What essentially happens is you collect it in multiple, Erlenmeyer flasks or test tubes, one after another, and each of these containers is called a fraction. So each of these sort of individual components is called a fraction. All right. So this would be fraction one, right? Because we collected it first, right? It came down faster first, and then this would be sort of fraction two. All right. So read this problem first and try out for yourself. You have a mixture containing three components, A, B, and C. Compound A is nonpolar, B is moderately polar, C is highly polar. Or you always want to circle or like underline like when they tell you about the polarities of whatever you're dealing with. Now, you perform column chromatography using silica gel as your essentially your uh, stationary phase, and then this is going to be a little bit different than what you've seen before. So we're going to start eluting with hexane. So first of all, our mobile phase is going to start off with hexane, right? Eluting just means that we're kind of like separating the components, the components in the mixture into like different sections, and we're essentially like draining them out, right? You saw in the diagram before how like we turned on our we rotated our cock stop um, that opened up the valve, and then it allowed the different compounds to like drain out. So eluting just means drained out in the context of chromatography. Now we first start off with a mobile phase of hexane, but then after we collect more fractions, we switch to a more polar substance known as ethyl acetate. This is more polar. Now, questions. What compound is expected to elute first when we're using hexane? Which compound will elute last, even after switching to ethyl acetate? And why do you switch solvents during the process? So feel free to pause the video to try and solve this for yourself. Well, let's say that if compound A is this blue color, let's say if compound B is this purple color, and let's say if compound C is this yellow color. All right, and we're actually going to label all of these on the diagram and predict, how far they will go. Okay. Well, first off, um, so we have like our whatever our mixture is in, whatever our mixture. Let's just say it's a green color, and then we start to elute it with hexane. All right, so we essentially start to drain out the different parts with hexane. Now, the nonpolar part, the nonpolar part is actually going to elute first, right? It's going to get to the bottom and it's going to drain out first because remember that we're first going to start eluting with hexane, right? If we first when we first use hexane, remember that when hexane travels down, hexane is nonpolar. So all the nonpolar things will start traveling down with it. Now, compound A is nonpolar, so it's going to be the first ones to sort of travel down. So essentially, um, when we use this hexane, it starts traveling down. What's going to happen is that the nonpolar part is going to travel down first, right? It's going to travel down first. Then what's going to happen is compound B is then going to travel after that because it's moderately polar, right? So it's going to be sort of attracted to the silica gel, right? It's going to have quite a bit of attraction to the silica gel. Remember, that's our stationary phase. That's the thing it's attracted to, right? So it's going to move a bit because it's only moderately polar, right? So it's going to be attracted to silica gel, but it's also going to move a bit. Now compound C is highly polar. Now compound C is highly polar, meaning that it's going to have the strongest attraction to the silica gel. So it's going to move the least, right? So you can imagine that compound C has a very high attraction to the silica gel, so then it's not going to move that much, right? So that's kind of the way you want to sort of think about it, right? Compound A is nonpolar, it's going to move the most. Compound C is, highly polar, so it's going to have the strongest attraction. And compound B is sort of in the middle, right? So it's going to be carried sort of in the middle of the distance, somewhat like this. All right. Now, so we have compound A as our answer here. Which compound will likely elute last even after switching to ethyl acetate? Which compound will sort of go last even after switching to ethyl acetate? A very polar thing. All right. So kind of the thing to know is that, well, notice how compound C is sort of in last place, right? So which compound will elute last even after switching to ethyl acetate? Well, it's actually going to be compound C that will elute last. Compound C is going to drain last, even if you switch to a more polar solvent. And the reason why is, well, remember that compound C has the highest attraction to the silica gel, right? Because it's the most polar, it's going to have the highest attraction to the silica gel. Therefore, even if we switch to a more polar solvent, it's still going to have a very strong attraction to the silica gel, right? So it's going to have like the most resistance, quote unquote, right? So kind of the thing to know is that the compound that matches up the most with the stationary phases sort of polarity, right? The thing that sort of matches up the most with it, well, that's going to have the highest quote unquote resistance to movement, right? It's going to want to stay with the silica gel the most, even if you use a different even if you use a different mobile phase. Now, why do you switch solvents during the process? Well, can you guys think of a reason why? Why do we switch solvents? Well, think about it. If we continue trying to drain this out with hexane, right? If we continue using hexane to try and drain this out, right? What's going to happen is the first thing that's going to drain out is, well, we said compound A, right? Because it's nonpolar and hexane is nonpolar. Compound B, yeah, it might take a little time, and that might also drain out. But compound C, that's going to take forever to drain out. Like, we got to be realistic, right? Compound A is nonpolar. Hexane is nonpolar. Compound C is highly polar. So therefore, compound C is just kind of going to stay where it is, right? It does not want to travel with the hexane. So you switch to ethyl acetate, which is more polar, because then it's going to be like faster. This process is going to happen faster. The draining is going to happen faster because all of the things that I want to get out are polar, right? So we switch sort of solvents because, well, so we switch solvents because compound C and B is polar. So switching solvents will allow the compounds. All right, so compound C and B is polar, so we decide to switch solvents so that this process would happen quicker, and to prevent them from just sticking to the silica gel the whole time, right?